Design a rate limiter system. On a high level, rate limiter is used to block calls to a system if it exceeds a defined threshold. For example, couple of examples to explain this, that a rate limiter from a very high level, what its functionality is to block the excess calls, and say, let's say a threshold is defined and all the calls that are excess of that threshold, that needs to be blocked. Couple of examples, like a user can't submit more than 5 posts per minute. So it would allow user, a specific user or each user, to post 5 posts within a minute. As soon as the user makes a post submission call as the sixth call within that minute, that needs to be blocked, and all the subsequent calls within that minute needs to be blocked. We have it on lead code. If you have seen, we make multiple submissions too frequently within a minute or so, and it throws exception and it throws error, basically blocking our submission. Can't claim rewards more than 2 times a week, etc. Like similar examples like this, and majority of system and the features in those systems definitely have rate limiting to it. So what are the benefits? Why all the systems and that too couple of features in those systems have rate limiting? It prevents resource starvation, and all API calls coming from different users get a fair chance to be processed. Under a DOS attack like denial of service, this system helps. All the big tech companies have it in place for large variety of their use cases, as we just discussed above. So with rate limiting, it prevents our servers from being overloaded, as we are blocking excess calls from specific users based on specific features. So it prevents our services from being overloaded. We also save cost if we are using some third-party services, which nowadays majority of applications are using third-party services behind the scenes. So limiting the number of calls which don't add much value is essential to reduce overall costs as well. Now let's gather requirements for the rate limiter system. We need rate limiter at server side. Okay. Flexible to support multiple use cases. Say rate limiting can be done. It needs to be flexible to be implemented on, let's say, user IDs, IPs, or other unique properties. So it should be like our system should be designed in such a way that it's flexible enough. Inform users about throttling. If we have blocked calls which made by certain users which have exceeded the threshold, we are throttling them. So we need to respond back to the user and let them know some information why their calls are blocked and not going forward or throttled, right? So these sort of information needs to be propagated by our system back to the user. Need to propagate right message, as I just explained, to users about how many requests they can make, why their request got throttled, so and so. A system needs to be highly available with as low latency as possible. Need to make it fault tolerant so that if any issue comes up with rate limiting system, it doesn't impact our rest of the system. Very high level design. Rate limiter is better to place in middleware at the proxy or API gateway layer rather than placing it alongside our API servers. So placing it at the front end doesn't add much value, as it's not, we can't depend or rely upon the information being propagated from the front end that could be hacked very easily. But placing it at the server and placing it at the proxy or the API gateway layer, there are pros and cons to them. With our current system, it's better to place it at the middleware, at the proxy API gateway layer, and we are not placing it alongside our API servers. Couple of reasons for that. Keeping it alongside my API servers means that API calls have reached our system and started eating up the resources. Also, any issues with our rate limiter can cause impact on our overall system as well. With keeping it at the proxy API gateway layer, we sort of use a fail fast mechanism. All the rate limited calls then don't even reach our API servers, and that totally makes sense. Also, it becomes much more easier to do config changes of our rate limiter or making updation or making updation to it without bothering our API servers. So without disturbing our API servers, without doing fresh deployments, with just config changes or little bit of changes with our rate limiter system. So we don't have to tweak our API servers or do fresh deployments. Also, it becomes much more easier to do the config changes if the rate limiter is present as a middleware at the proxy or the API gateway layer as a proper segregation between our rate limiter system and our API servers. Let's see it, what would happen from a very high level. For example, let's say this system allows 3 requests per minute. So the first request, it would go through and be passed by the rate limiter system, and it's coming under a minute and reaches our API servers. Let's say second request also comes within a minute and it gets also passed. Third request again comes under a minute, it would also get passed. Now when the fourth request comes and we are still under a minute, our rate limiter system need to block this request, and it shouldn't allow that particular request by the certain client to reach the API servers, and it needs to propagate specific message and information back to the client why this fourth request under a minute got blocked. Before discussing all of this, let us first see a couple of algorithms which are used and are quite highly popular for the rate limiter system. First is the token bucket algorithm. Token bucket is a container. Consider it as a water bucket. Think about that. It's a container that has a predefined capacity. Okay. Tokens are put in the bucket at preset rates periodically. Once bucket goes full, no more tokens can be added, and if the preset rate is happening periodically of filling the tokens, those tokens, if the token bucket is full, will eventually overflow from it. So we can see there are two dynamic fields with us with this algorithm. One is the token bucket capacity and the other is the refill rate of the tokens happening periodically. What we just discussed above, the same thing is explained over here. This is the bucket with the predefined tokens, predefined capacity of tokens to it, and this is the refiller, which is refilling the tokens at a certain rate called as the refill rate. If the bucket is full, all the tokens that further get filled by the refiller would definitely overflow. This becomes token bucket with capacity equals 4, as we can see 1, 2, 3 and 4, and refill rate per minute also 4. So 1, 2, 3 and 4. Let's take this example to explain this algorithm a little bit more in depth. So the refill rate per minute is 4. So every minute this bucket, this token bucket will be filled with 4 tokens, 4 new tokens. If the bucket is full, those fresh tokens will overflow. If the bucket is having lesser tokens or it's empty, the refiller would fill it with the fresh tokens. Make sense? So let's say initially the bucket is full. First request comes at 1 minute, that gets succeeded. Now second, third and fourth request comes together like as a burst of requests at 1 minute and 20 seconds, and they all get succeeded. Why? Because capacity is 4, and let's assume on a very simpler level that each request is consuming 1 token from the bucket container, from the token bucket, to be processed and fulfilled. Now after these 4 requests, bucket goes empty till we hit 2 minute, as we started from 1 minute. So basically till we hit the next minute, so that the refiller can play its action and refill this empty token bucket with 4 new fresh tokens, so that the refill of 4 more tokens can be done. Now if we still are at 1 minute 40 second and the same client makes another request, then that needs to be blocked, as I have mentioned here, because there are no more tokens left for this request to make it processed in our token bucket. Now let's say 1 whole minute gets passed and now we are at 2 minute 1 second. So the refill rate of adding 4 tokens per minute, so the refilling has happened somewhere over here, right? So let me mention refilling happened here. And what it did is it filled our empty token bucket with 4 fresh tokens. Now at 2 minute 1 second, let's say 2 requests come sort of as a burst of request, and it will pick up 2 tokens from the freshly added 4 tokens, and these will be processed. And still 2 tokens will be left in our token bucket. We expand this algorithm to have different token buckets with different capacity and refill rate for different use cases. So this token bucket with dynamic values for token bucket capacity and the refill rate. So it can be different for different applications based on their use cases, and even within the same application for different use cases or different features, it can be entirely different values. A different token bucket for example, let's say a different token bucket for posting content as one feature, placing orders as another feature, so and so on, making payments and so on. Here each user will require, so for these two use cases, let's say our app has these two use cases where we need rate limiting, and the implementation is token bucket algorithm for that rate limiter system. So here each user will require 2 buckets each for both use cases of posting content and placing order. Now each algo here, which we'll be discussing with rate limiter system, has its pros and cons. For token bucket, good thing is it's quite easier to implement and understand. It allows traffic bursts to go through and get handled if tokens are present in the token bucket. Limitations are it's quite a difficult thing to tune them properly, values of both token bucket capacity and refill rate, so that the overall system behaves properly. Second algorithm is leaky bucket algorithm. This is quite similar to fixed token bucket algo as we discussed above, just that the requests are processed at a fixed rate. It's implemented with use of a queue, which works on FIFO principle, which is first in, first out. It's quite easier to understand. Request comes in and system checks. So let's say request comes in and system checks if the FIFO queue acting as a container here is full or not. If it's full, request is dropped. If it's not full, request is added to the queue, and it keeps on getting processed at a fixed rate. Seeing from the example to understand it better, let's say user is making requests. So we check if the bucket or our FIFO queue is full or not. If it's full, it comes to the yes part and the request gets dropped. In some time, we'll also discuss what needs to be propagated back to the user on throttling the request. If the bucket is not full, it goes to the no flow and the request gets added to our FIFO queue. And over here, it's being processed from the FIFO queue at a fixed rate, and it's like reaching our API servers to be processed further. This is quite useful for the use cases where a fixed outflow rate is needed. Couple of limitations. This algorithm doesn't support well with burst of traffic, unlike what we saw above with our token bucket algorithm, as a burst of request might fill up the queue quickly, and all recent requests might get rate limited. Also here we have again 2 params as well, and we need to tune them both, which is the queue capacity and the outflow rate. So again, similar to token bucket, it's quite difficult to tune them properly so that the overall system behaves properly. The last algo which we will be discussing is the sliding window log algorithm. There are a couple of more algorithms as well. Feel free to dig deep and read in depth about them as well. But yeah, these 3 are quite important and are widely used by a lot of real world applications. With sliding window log algo, this algorithm keeps track of request timestamps. This data is kept in cache, such as Redis sorted sets, for a faster updation of the addition of the timestamp and for a faster retrieval. When a new request comes in, we remove all the outdated timestamps from the Redis sorted set, and if this new request is approved to pass through, and not get rate limited, this gets added to the sorted sets. If the number of requests and their added timestamps in a certain window is exceeding, request is dropped, else it gets added. Quite simple enough that if in a certain window of timestamps the threshold has reached for the number of requests that can go through, the request is dropped, else it gets added and gets processed. Also, while addition of that request, we only maintain in our sorted set the timestamps for that particular window and keep on removing the outdated timestamps as well, which are outside of that window. For example, let's see it from a system and an example. We allow only 2 requests, let's say, of placing an order per minute per user ID. So our system says of placing an order that a particular user per minute can only make 2 order requests. So let's see, user ID at 1 minute 1 second, that particular user ID, let's take it as X, makes a request. We will add it to our Redis sorted set. This timestamp, I have kept it quite simple enough of 101 to reflect 1 minute 1 second. Next request comes at 1 minute 30 seconds and that gets added to the sliding window log as well. Now we have reached our threshold already of placing 2 order requests per user ID per minute. Now let's say the same user X made another request at 1 minute 50 seconds and we went ahead. We saw already in that 1 minute window from 1 minute 50 seconds to 50 seconds, as we can see here, already got 2 requests, which we can see from here as well. So we say it already has 2 requests, it has reached its threshold. So this basically request gets dropped. Now next request comes at, let's say, 2 minute 20 seconds now. So now the 2 minute 20 second forms a window from 1 minute 20 second to 2 minute 20 second. So requests that are outdated, the timestamps that have been outdated, like outside of 1 minute 20 second to 2 minute 20 second, is for the request that came at 1 minute 1 second. So we basically remove that, as I discussed above, that we remove the outdated timestamps as well. And then we just have one request with us in that window of 1 minute 20 second to 2 minute 20 second. So this request also gets parsed. And similar thing I've written here, 1 minute 1 second request gets removed being an older entry now or an outdated timestamp as compared with the 2 minute 20 second request. This rate limiting algorithm is quite accurate as it's based on timestamps. Downside is that storing of all these timestamp logs consume too much memory at Redis. So it's quite accurate as it's dealing with timestamp. That's the upside, but a little bit of downside is that we need to store and compare all these timestamps and maintain that with Redis sorted sets. So the memory consumption is quite on the higher side. Let's revisit the design now, what we left early on. And we said that we will discuss it again once we have covered a couple of rate limiting algorithms. Basic idea of rate limiting is simple now. We need a place to store the counter, makes sense, and keep then track of it. Then also we need a place to compare these counters against our rate limiting rules. Makes sense? That we need to keep on accumulating these counters for the request for the users that they are making so that we can see if they have reached the threshold or not. And then we also need a place to store the rate limiting rules. What are the rules? What are the allowed values? What sort of algorithm to use? Like, are the rules per minute, per week, per day based or something like that? So we need a place to store these rate limiting rules as well, with which our counters will be compared. These counters now can be of anything, say user IP, user ID, etc. So the key can be anything, user IP, user ID, and so on, as we discussed in our requirement gathering as well, that we need our system to be flexible enough to store and handle all these values. If the counter is larger than the limit, request is disallowed. If the counter is within limit, request is allowed. Pretty simple. We can use Redis to store these counters. So with Redis, what will happen? Client makes a call. We have this rate limiting middleware at the proxy or the API gateway layer. If the request is allowed, it basically fetches the counters from the Redis, then compares with the rate limiting rules. If the request is allowed, then it increments the counter and the request goes to the API servers. If the request is not allowed, as this request is breaching the threshold, then we don't do anything with the counter, but we drop the request and it doesn't reach the API servers. Now, by discussing this, we can see two more things we would need further to discuss upon. Rate limiting rules creation. We haven't discussed them yet, with which we are making the comparison of these counters and where to store them. Also, the second thing which we left early on is when rate limiting hits and we throttle the request, how to respond accordingly and what to respond with back to the user so they get proper information about why the request got dropped. Rate limiting rules. Rules should be such that we can have different rules plus config based on domain, use case, say messaging, post creation, auth, etc. As we discussed in the requirement gathering phase, we need to support and store rules in such a way that we can expand on the rules based on the features that our application supports, such as it supports messaging, so a couple of rules for that. It supports creation of posts, so a couple of rules for that, couple of rate limiting rules for the authentication part, and so on and so forth. We also need to support unit, say it can be per second, it can be per minute or per day. Let's say allowing 5 messages per minute, 5 times authentication per second, and let's say 10 times post creation per day, and so on. And its value as the limit of requests allowed over that unit, as I just discussed. So, how it would look like? Say we need to have the domain or the use case. Then we need to have unit as, let's say, have it as minute. And then if I have the value as 5, so this means that is 5 requests are allowed per minute for this specific use case or domain. We can store such rules in a persistent store and cache them to Redis for fast retrieval and then compare them with the counter which we are already also storing in Redis itself. Redis config with these rules can be somewhat similar to, it needs to have, let's say it has route, say API level or domain, which is the use case, defining these rules, what it's being used for, let's say a certain use case or for a certain API, then the type, which is the algorithm being used. We can have key for scope, which is, let's say, per user level, unit, as I just discussed above. For example, let's say it's 1 minute. So per minute, per second, per day, and so on. Then the request allowed per unit, let's say 5. So this system is allowing 5 requests per minute per user with this specific algorithm for this specific API or use case. And then we can also have action which defines couple of enums. Let's say on being rate limited, on being throttled, do we need to, like if it exceeds the threshold value, do we need to retry? Do we need to throttle, or do we need to push it to some queue if the use case is quite important and we don't want the request to be dropped? Maybe we can push it to a queue or have retry mechanism in place so it can be tried again after some time, or can be consumed from the queue and processed again. Or do we need to throttle and return back some important information back to the user? Now, what needs to be responded back to the user? So let's see what we can respond back. So depending upon our use case, we can plan to respond back accordingly when rate limiting hits, when we exceed our threshold for the requests that are allowed during a certain window. So we can return 429 status code with too many requests, and user can try again after some time. If the use case is important, as I just mentioned above, then we can implement a retry mechanism in place or push these requests to a queue to be consumed and tried again after some time. Now, while responding back 429 plus too many requests back to the user, we can also send back X rate limit headers with, let's say, remaining requests, total requests allowed, and retry after, etc. So a couple of these headers to propagate back some more information from our backend, and then this can be worked upon at the UI side to form a certain message, as I have just mentioned here. So message can be formed and sent back accordingly and shown back to the user based on what values these headers store, like got back. Now with all of this, let's see what our overall system will look like with rate limiting at the API gateway or proxy layer. Then if it being passed or failed, then if our request is being failed, if it hits the threshold, what to do with the request that we have already discussed, how the rate limiting rules are being stored in the DB and then they are reaching the Redis cache, and how the counters are also being stored in the Redis cache. So we have the client, it makes a request, it reaches our rate limiting middleware. If so, firstly, rate limiting middleware will check for the counters in the Redis for that specific key for that client and the use case or the API it's trying to make request for. Then in the Redis, we have rules as well. So the rate limiting middleware will fetch the rules as well, which will have the threshold, unit, scope, and couple of other things, action, and couple of other things with which the counter would be compared with. How these rules reach Redis? We can have these rules persist somewhere. Let's say it's being persisted in a DB, and we have our workers which pull it from the DB at certain intervals and then keep on updating in the Redis cache. Then fetch plus update counters happen if the request passes, it reaches the API servers. And on fetching and comparing, if the counter has reached the threshold, then we need to fail this request. So we send back 429 with the rate limiting, X rate limiting headers. So we throttle and respond back with 429 plus X RL headers. And depending upon the use case, we can also have like retry mechanism or push it to a queue as well, or push it to a MQ for it to be consumed and processed later on, depending upon the use case.